Big Idea 6 is all about equilibrium, specifically equilibrium as they relate to general reactions, acid-base equilibrium, including titrations, weak acids, weak bases, etc. We're going to break Big Idea 6 up into two parts. This is just part 1 that focuses on general equilibrium, including reaction quotients, equilibrium constants, ice tables, and solubility products. So, just to remind ourselves, most reactions that we've learned occur from left to right, where we have some reactants that get converted into products. Okay? But the majority of reactions, nearly all reactions that occur, don't just occur in one single direction. They actually occur in two directions. A forward reaction from left to right, where reactants are turned into products, and a reverse reaction, where products are turned into reactants. We've reviewed the idea of rates, how we can measure the rates of these two reactions, of the what we would label as the reverse rate and the forward rate. We can also quantify concentrations of different compounds when both of these reactions are happening. So, the main way that is done is by calculating something called the reaction quotient. The reaction quotient, reaction quotient is a ratio. Remember, quotient is the answer you get when you divide two things, that we abbreviate with the capital letter Q. So for any given reaction of AA plus BB going to CC plus DD, where A, the little lowercase letters are the coefficients of the balanced reaction, we can write the equilibrium constant Q based on any of these expressions, and it's always going to be the products divided by the reactants. More specifically, it's going to be the concentration of reactant C to the power of C times the concentration of reactant D to the power of little d, from right here, the coefficient, divided by the concentration of A to the little a times the concentration of B to the little b. Again, just to clarify, the lowercase letters are the coefficients that we find here, 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 and here. So we can do this for any reaction that is reversible, that goes in two directions, and we can determine what the reaction quotient is at any specific time. Now, when we're at special conditions, the reaction quotient has a new name, and it is called the equilibrium constant. So that occurs when a system is at equilibrium. Okay? So what is occurring at equilibrium? Okay, we'll break down the word equal. Something is equal. What's the thing that is equal? The rate of the reverse reaction is equal to the rate of the forward reaction. Those rates are equal. So for the reaction A and B, the rate at which A is getting turned into B, let's say, is 2 molar per second. If we're at equilibrium, B is also getting converted back into A at 2 molar per second. So if those rates are equal, we also know the concentration of A and B is constant. They're not changing. Because for every 2 moles per second that A gets converted into B, 2 moles are also getting converted back into A. So the amount of A is not going to change. The concentration of A and B do not have to be equal to each other necessarily. They don't. But they do have to remain constant over time. The last thing about equilibrium is that it is dynamic. It does not stop. Once you've reached equilibrium, the reaction does not stop. So if we're at equilibrium, we no longer use the letter K to represent, the letter Q to represent the reaction quotient. We use the letter K, and this is called the equilibrium constant. It's determined the exact same way. So for this particular reaction, it would be the concentration of B to the power of 1, because the coefficient here is a 1, over the concentration of A. That's how we would determine the equilibrium constant for this reaction. This would be K sub C for concentration. There are a bunch of different equilibrium constants that we're going to review. In this video, we'll talk about the equilibrium constant for gases at pressure. We'll talk about KSP, the solubility product, equilibrium for a solid dissolving into its ions. Later in part 2, we'll talk about Ka, Kb, and Kw, which is the acid dissociation constant, the base dissociation constant, and the ionization of water. They are all equilibrium constants that are calculated by the same formula on the previous slide. The one thing we want to know for sure always, there are no units for capital K. Don't get confused with a rate law. There are units for the rate constant in a rate law, which we've reviewed already. Okay, you know, something like this. This does have units. But for an equilibrium constant, no, there are no units. So let's get some practice writing those. So given this reaction above, solution of ammonia is dissolved in water, essentially, to produce ammonium ions and hydroxide ions. How would we write the equilibrium constant equilibrium expression for this? Well, K would be equal to the concentration of the products, so NH4 plus to the power of 1, because the coefficient here is a 1, times the concentration of OH minus to the power of 1, coefficient here is a 1, divided by the reactants, so the concentration of NH3 to the power of 1, because the coefficient here is a 1. And that's it. I'm done. I don't include H2O. And so why is that? Well, if we remember, when we're writing equilibrium expressions, okay, K does not include pure substances. So it does not include liquids or solids. So if liquids and solids ever appear in a reaction, like they do here, that compound is not shown, it does not matter in the equilibrium expression. Okay. Let's look at another example. In this reaction, we have hydrogen sulfide gas reacting with oxygen to produce water vapor and sulfur dioxide gas. Well, the interesting thing here is we have all gases. So when we have all gases and we write the equilibrium expression, it's not Kc anymore, it's now Kp. And so we don't talk about the concentration of a gas, we talk about its partial pressure. So we would say Kp is going to be equal to the partial pressure of H2O to the power of 2, from right here, times the partial pressure of sulfur dioxide to the power of 2, from right here, divided by the partial pressure of, the partial pressure of H2S to the power of 2 times the partial pressure of oxygen to the power of 3 from this coefficient. So remember, I've talked about this in class. We've made this mistake very frequently on free response problems in the past. If you're given gases and you're asked to write the equilibrium expression, you need to write it with the partial pressures. You cannot write it as concentration and write Kc. That doesn't work if you're given gases. It's not the same value. Okay. So what is special about the equilibrium constant? Well, we know that when K is greater than 1, the products are favored. Because in order for K to be greater than 1, we know that the numerator, this value, must be greater than the denominator, this value, to make K greater than 1. So we know that if K is greater than 1, the products are favored. The reaction is spontaneous to the right in the forward direction. If k is less than 1, on the other hand, that means the denominator is a larger value than the numerator. So we have like 1 over 2, for example. And now we would say that the reactants are favored. This reaction is spontaneous in the reverse direction, to the left. Okay? Using that information, we can predict how a reaction will shift if it is stressed. And the way we do that is using Le Chatelier's principle. We're going to talk about it qualitatively first. So let's say we have this reaction here. We have nitrogen gas reacting with hydrogen gas to produce ammonia gas. And the enthalpy of this reaction is negative 92 kilojoules. Okay? Well, let's say we stress this reaction. There's a bunch of ways we could stress it. Okay, we could change the concentration. Okay, so let's say we added more N2. How would this reaction shift in order to get back to equilibrium? Well, if you remember our seesaw method, okay, we're at equilibrium. If we add more N2, N2 is a reactant, so this side is going to drop. So now our teeter-totter is going to look something like this. So in order to get back to equilibrium, the reaction is going to need to make more product, make this side heavier to bring it back down. By making more product, the only way we can do that is by taking some of the reactants we had and turning them into product. So the reaction, we would say, would shift to the right. Instead of adding more N2, we could remove H2. So if we remove a reactant, we need to make more to get back to equilibrium. So the reaction would now shift to the left. We could also change the temperature. Okay, so let's say we added heat. We increased the temperature of this reaction. Which way is it going to shift? Well, we have to figure out now, is it endo or exothermic? To check yourself real quick, you should be able to know immediately, since this is a negative value, it's exothermic. So heat is essentially a product. So now we use the same rules as before. Okay? If we're adding more heat, we're adding more product. So we're going to have to get back to equilibrium, we're going to have to shift to the left. Okay? So this reaction would shift to the left. We also could change the pressure. Okay? Now the rule for the pressure does not use the teeter-totter. Remember, the rule is if you increase the pressure, it shifts to the side with less moles, because that has less of a stress on the system. If we decrease the pressure, it would shift to the side with more moles. So in this case, let's say, for example, we increase the pressure. We know we're going to shift to the side with less moles of gas. Which side has less moles? Well, the reactant side has 1 plus 3, 4 moles. The product side just has 2. Heat doesn't count. So the side with less moles is the right side, the product, so this would shift to the right if we increase the pressure, and to the left if we decrease the pressure for this particular reaction. Those are the qualitative predictions we have to do with Le Chatelier. What about quantitative with numbers? So let's say we have the exact same reaction as before, nitrogen and hydrogen gas reacting to form ammonia, and we're at equilibrium. What if we were given something like the equilibrium constant for this reaction is 2? And then we're also given that the concentration of N2 is 1 molar, the concentration of H2 is 2 molar, and the concentration of NH3 is 2 molar. I just made those numbers up. Okay. Now, I want you to recognize that I did make an error here. I'm representing these values in molarity, even though these are gases. I know that. We should be representing these as partial pressures, but for the problem's sake, let's just assume that it's okay. Well, first we want to figure out, are we at equilibrium? Well, remember, if we're at equilibrium, we know K is equal to Q at equilibrium. So let's find out if that's true. Is Q equal to 2? Well, Q is going to be equal to NH3 squared over, you should be able to do this instantaneously, this reaction here. So it's going to be 2 squared over 2 to the cubed times 1, which is going to be equal to 4 over 8, which is equal to 0.5 or 1/2. So right away, is this reaction at equilibrium? Well, Q is not equal to K, so no. So now the idea is to figure out which way is it going to shift. Well, if Q is less than K, that means the value of the denominator, or the numerator, is not big enough. It's not a big enough value. We haven't made enough products. So if Q is less than K, we're going to shift to the right. Okay? And if Q is greater than K, that means we have too much products. So we're going to shift to the left. So we can figure that out quantitatively by calculating Q and comparing it to the value of K. What we could do next is, given these concentrations and this equilibrium constant, what would the concentrations be at equilibrium? Let's go ahead and look at that really quickly. Well, the way we do that is if we have this reaction N2 plus 3H2 equilibrium 2NH3. And if we know the values from before of N2 is 1 molar, H2 was 2 molar, and NH3 was 2 molar. We know the initial concentrations, okay, are 1, 2, and 2. How much are they going to change by? Well, we said since Q is less than K, it's going to shift to the right. So the amount of reactants is going to drop, and the amount of products is going to increase. Since the coefficient of 2 is up here, this needs to be a 2. And you hopefully could have checked my error here. This needs to be minus 3x. So the equilibrium concentrations would be 1 minus x, 2 minus 3x, and 2 plus 2x. Okay. Then we know the equilibrium expression is K is equal to NH3 squared over H2 cubed times N2. We would plug in all these values. Boom. Here, here, and here. And set this equal to K, which we said was 2 from the page before. Again, I just made up these numbers. And we could solve for x and then determine what the concentrations are. We'll get more practice with those in the next video, but I just wanted to refresh your memory on ice tables really quickly, the setup. What if a reaction is multi-step? So let's say, for example, we had A plus B is in equilibrium with C. That has its own equilibrium constant we'll call K1. And let's say C is then in equilibrium with D plus E. It has its own equilibrium constant K2. What's the net reaction of these two? Well, if we add them together, we get A plus B is in equilibrium with D plus E. So it's like if we had a mechanism, for example. How do we figure out K of the overall reaction? Well, it's pretty simple. K of the overall reaction is the products of all the equilibrium constants before it. So K1 times K2. If there were 3 steps, it would be times K3, and on and on and on. Now, one thing to be aware of, this is different for enthalpies. Remember, for enthalpies, when we did delta H of a reaction, it was equal to delta H1 plus delta H2 plus delta H3. That is only true for enthalpy. It is not true for equilibrium constants. They are multiplied when it's equilibrium constant. And I'm not going to go over the derivation of that right now. Just got to remember it. Last thing we're going to talk about in this video is the solubility product. So remember, solubility product is KSP. And basically this is a measure of how much a solid dissociates, okay, or dissolves. A solid dissociates, okay. So for example, if we took the compound calcium fluoride, okay, and we dropped it into water, it's going to be in equilibrium. It's going to dissociate into its ions. So calcium is a group 2 metal, so Ca2+, aqueous in water. And we have fluorine, which is 1-, 2 of them, aqueous in water. this is going to be in equilibrium. So how would we write the equilibrium expression for it? Well, it's always products over reactants. So Ca2 plus, oops, excuse me, I'll put that inside the brackets just to make it a little clearer. Ca2 plus times F minus squared divided by nothing, because this is a pure substance, it's a solid. So this would be the equilibrium expression for the solubility product of calcium fluoride. Okay. What if we had another example, like silver chloride? So silver chloride has the formula AgCl. If it's a solid, it's going to dissociate into its ions. Silver always forms a +1 ion, aqueous, and chloride ion would dissociate. Okay. Let's say you were given that the KSP is equal to 1.6 times 10 to the negative 10. Remember, when we're thinking about KSP values, they should always be very, very small. They should always be times 10 to the negative something, because that means they're much, much, much less than 1, which makes sense because they should definitely favor the reactant side. They should favor the left side. They don't dissociate very much. The only time they will is when we start talking about strong acids. Weak acids will be the same thing. They'll be much less than 1 for Kas. Well, we know that the KSP, 1.6 times 10 to the negative 10, is going to be equal to the concentration of silver ions times the concentration of chloride ions. Let's say at equilibrium we drop in some silver chloride into water. What's the concentration of each ion going to be at equilibrium? Well, all that it depends on is the KSP, because we know that both of these are unknown. They're essentially both x because it's a 1-to-1 ratio of each element. So it's essentially like x times x is equal to 1.6 times 10 to the negative 10th, which is essentially equal to, that's a 10, x squared. So essentially to solve for x, it's just the square root of this number, which gives us 1.3 times 10 to the negative 5th molar. So that is going to be equal to the concentration of both chloride and of the silver ions at equilibrium. You could also be given problems where it's not a 1-to-1 relationship and there's like an exponent up here or something, and you have to play around with that. Or you could be given the concentrations, given these instead, and asked to calculate what the KSP is. We'll do some practice with that in class. The last concept we need to review is something called the common ion effect. So let's say we have the same situation as before, AgCl dissociating into Ag plus and Cl minus. Both of those are aqueous. We said the KSP was equal to 1.6 times 10 to the negative 10. Well, let's say we had a beaker, okay, full of water, and we dropped in some AgCl. We know it's going to dissociate, it's going to get to equilibrium, and we know the concentration from the problem before of each ion, Ag plus concentration, is going to equal the Cl minus concentration, which was 1.3 times 10 to the negative 5th molar. But now let's say, just for fun, we added in some NaCl. What's going to happen? Well, NaCl is going to dissociate into two ions, Na plus and Cl minus. Is that going to affect this equilibrium? If so, how? Well, Na plus, that doesn't appear anywhere in this reaction, so Na plus plays no role. But Cl minus is totally present as a product. This is a common ion from NaCl and AgCl. They have a common ion. So by adding Cl minus, essentially what we're doing is we're adding extra product. So it's the same idea as before. What's going to happen to equilibrium if we add more product? Kind of think about your teeter-totter. We've now added extra product, so this side's going to drop. So now our teeter-totter's off balance. So to get back to equilibrium, we're going to have to shift to the left. So the amount of AgCl solid is going to increase, and the amount of Ag plus is going to decrease because it's a product getting used up to make reactant.
So we might be asked to, predict what would happen with the common ion effect. But again, remember, this is just the same exact concept with Le Chatelier's principle that we've covered before. So as the first half of Big Idea 6, we'll talk about the second half tomorrow in the next video.